Thank you for joining us today. I'm delighted to be joined by Amelia Hargreaves from the Queen Elizabeth Hospital and Josh Kirstner from 3D Systems. Thank you both for joining us today. We're going to discuss how 3D technology has assisted the Queen Elizabeth Hospital in performing a maxillectomy. I'm Leanne Jones from Or3D, and I'm going to be talking through this case with Amelia here, and obviously we're going to be speaking to Josh as well from 3D Systems about the haptics and freeform. So before we go into the case, I think it'd be quite nice to have a chat about your role as a biomedical engineer, Millie, if that's okay.
Yes. So I've been at the QE hospital now for 3 years, and I work in the maxillofacial prosthetics team as a biomedical engineer. So I'm purely employed to do all 3D planning for the maxillofacial department, but also other departments that we work for throughout the hospital. So this can range from dental work to reconstruction for cancer cases, like this case study, cranioplasties for neurosurgeons, orthopedic work as well, and work at the Children's Hospital as well.
Fantastic. And are you the only biomedical engineer at the hospital?
Yes, so our department's very lucky. We are the only department who can have an in-house biomedical engineer, which is why we are able to work for other departments within the hospital, because it's a shame really to have all the skill set we've got and not share it. So we have our own printing in-house that we can offer to other departments for biocompatible printing for surgical cutting guides, as well as models for visual surgical planning.
Fantastic. And you work very closely, obviously, with the surgeons. So before you go to plan, for example, in this case, how closely do you work together?
So all the cases I do are coming directly from the surgeons themselves. So they will contact me with a request form or email, or just pop in person, which is the advantage of being within the hospital. They will give me the patient details, what they need for that patient, how I can help, and then I'll go away, work on the planning, and then throughout they will pop back, see if they approve of the plan, if they're happy, and then it can go back to them. If not, we can change, and then it will all get printed, and then I also can go to theatres as well and see the actual planning happen. So that also allows us to get feedback from when we're actually what we've done is working, and if we need to change anything for future cases, it can implement it straight away with the surgeons telling us there and then what's good and not good.
Fantastic. Josh, would you mind just giving us an overview of the Haptic Touch X and Freeform Plus software, please?
Sure. The haptic device is a reverse robot in a sense that allows you to interact with objects in 3D space. So when you push into an object on the screen, the haptic device actually pushes back and gives you what that tactile feedback is of that object. The Freeform software is a voxel-based modeling software was specifically designed to use with a haptic device, and it allows users to offer a level of creativity and development that is not achievable with any other CAD software. The voxels react in real time, so when you push into a model, the voxels update as soon as you push or pull onto that object in the virtual space. And it's the supreme software, in my personal opinion, for modeling with organic shapes, specifically human anatomy, or even organic anatomy, like figurines and toys of that nature.
Fantastic. So, Millie, I think you said you've used this for the whole time you've been a biomedical engineer at Queen Elizabeth Hospital.
Yeah.
And how do you find using the software and the haptic?
Very user friendly.
Yeah.
I think that's the first thing I noticed, having no experience of it. When I first started, I quickly was able to pick up how to use it, all the different tools, what did what. It was quite easy to build on my knowledge and just continue to still find new ways that I can use it every day within different work that we do.
Okay, brilliant. So if I were to say, before you used the Haptic and the Freeform software, traditional methods, how much longer would this take you to do a virtual plan for the surgeons?
So years ago, when they used to only have the ability to 3D print the bone itself from the CT, so not always actually design guides, they would print that bone off, and then in the lab they would have to manually mould the metal guides to fit the bone, which involves a lot of different skills and techniques from our lab technicians in welding those guides together, which would take hours and days longer compared to now. A plan can be done in a few hours' time and printed overnight, and then it enables the next day the labs to do their part, and the whole case can be sent off within 2 days for sterilisation, ready for theatre.
Wow, that's pretty amazing. So let's start talking a bit about the case study, the maxillectomy. Let's start off, if you wouldn't mind, just define maxillectomy for us, for those who don't know.
So the maxilla is also known as the upper jaw. So it consists of different parts. So there's the cheekbone, the nasal area, the orbital rim, and also the roof of your mouth, which all encompasses into being the maxilla. So when someone has a maxillectomy, they can have a hemi one, where, like this case study, only half is having to be removed. It could be full, so both right and left sides, or also just partial, where just the area affected by the cancer normally is removed.
Okay, and we've got a few models here, haven't you, that you've brought in today?
So this is the model that was obviously involved in the case study. So here's your maxilla area. So this is what it would look like when there is no problem, and this is the reconstructed side. So this is showing the pelvic bone in place that's then been shaped for the orbit and the nasal area, and then the colours are for the different plates that would have been bent to hold this new reconstruction in place. So they're called mini plates, so they're just drilled into the bone and onto the part of the maxilla that's still there. And then this plate is an orbital floor plate that's been made in the lab. So it's been moulded to match the non-defect side. So the Freeform software was used to mirror the non-defect side over to the defect, so that a little plastic piece was printed, which then allowed this metal titanium plate to be moulded onto that, and this matches the natural shape that was there before.
Fantastic. Okay, so let's have a little chat about the case and what we were presented with here, with the tumour and so on. If you'd just like to give us an overview, Millie.
Yeah, so this was a gentleman who was 40 years old, and he had an ameloblastoma, which is a kind of cancer which originates in the jaw or the upper jaw. So for this patient, it was in the upper jaw. So it needed to be removed, and as you can see from the case study, it's rather large. So to start the initial plans, we use the CT scans of the patient. So everything that we do is bespoke to each individual, so all the guides are made for each patient, so nothing is mass produced. So using Materialise Mimic software, I can convert the CT scans into the models that we need to create the plan, and also use the MRI to create the tumour, because tumours show up a lot better on an MRI. A CT shows bone as high quality, but the tissues can often get lost. So we can use both scans to really get the most out of digitally planning, and we can overlay these onto each other so that we can see the orientation of the tumour within the bone models that we have.
Okay.
So once we've separated the bone models into the maxilla and the lower jaw, and we've got a model that is purely the tumour, we then go into Freeform software then to start the whole process of doing the cuts for the resection and then designing the guides. So once we've gone into Freeform, we normally this is where I would involve the surgeon. So they would confirm what osteotomy cuts, which is the resections where the bone is going to be cut. So they would give me that information, and then they would also say what bone graft they want to use for the plan. So this plan was made with the pelvis, also known as the DCIA in the medical terms of when we're planning these cases. So Freeform, then the planes are used to cut the bone.
Okay.
So that will then leave us with the defect. And then we can start using all the different tools where we can manipulate the pelvis into the space of the defect. So generally just moving it, rotating it so that it's sitting nicely within the defect model. And obviously that's the sort of advantage of the haptic as well. It gives you that ability to move it freely within the 3D space and check all the different angles of where it's sitting against the native bone that's still there. Is it flush? Is it going to produce a nice aesthetic outcome?
Okay.
All those kind of things.
And once you've removed the pelvic bone, is the patient okay without that bone, or is there something have to be replaced?
So the space that is left in the pelvis is fine. It can be functional. It's not affected in that way. Mm-hmm. Sometimes it can leave a divot in the person's skin if the skin starts to sink into the defect.
Okay.
We have started to recently implement a titanium mesh that can be put over the hole. So that again, that is we would print out the pelvic bone of that patient, and then in the lab they would use the titanium to create a mold and a mesh that would then be slotted straight into that patient, and it just fills that gap, and it allows the surgeons as well to attach the mesh to it, which can prevent hernias and problems after surgery.
Is it then a case of refining and obviously fitting that to the anatomy of the patient? Is that correct?
Yeah, so before you remove the cuts, I position the pelvis as a whole into the defect space. Mm-hmm. It just allows you to get it completely right to those resections before you make any cuts, so there's no spaces either side of the bone graft, because what you really need is contact between the new bone that's going in for the reconstruction and then the bone that is still obviously there, because that is allowing integration once the patient is starting to recover. Okay. That will keep the bone alive. So it's always best to cut it to the exact same resection cuts that have been made already to that defect.
Okay.
So once those cuts have then been made and it's positioned in its final position, we then would move on to the guide design then.
I see. Okay. Okay, so moving on to the cutting guides, were there any challenges here when creating the guides?
Yes, so the cutting guides are bespoke to each individual, mm-hmm. and each individual is different anatomy. So for example, one of the problems we face is muscles in a person. So muscles can vary from different widths, and it's not very clear on the CT scans that we have how thick everyone's muscles are. So when designing the guides, we always provide an offset on the bone before we even start the initial guide. So we normally do an offset of 1 mil in Freeform on the bone. This then allows for anything that can't be stripped during surgery. So sometimes there's periosteum which still sits on the bone, but it still guarantees that the guide will fit over the space. I suppose a problem you could face is if a person happens to have more than the 1 mil offset, which is rare, it would cause the guide to not fit very well in theatre, but it's very rare and it's hard to dictate that for everybody really. The 1 mil seems to be a general rule that does work. For all the cases that we do.
So if it didn't fit, what is the process?
So the surgeons could try and strip the bone more, but again that is taking more time, mm-hmm. and it's not great. It can cause the bone to deteriorate slightly.
Right.
It's also longer that the bone may be out of the body if it's already been detached from its blood supply, which you really want to reduce. You don't want much time that it's not got a blood supply. So that is the whole advantage of using these guides. It's meant to be quicker and easier in terms of they can guarantee that getting an accurate result before they put it into the reconstruction.
Wow. And what is the time frame?
Roughly, I think you've got about an hour of it being detached normally from the blood supply. So you really need to do your cuts quite quick and get it in, and then attach back to the new blood vessels, normally in the neck for these kind of cases.
Could you tell us a bit about the design of the guides?
So for the DCIA, the pelvis, we normally provide 2 cutting guides. So there's an initial guide when they are just removing the pelvis bone that we want from the actual pelvis. So this guide is quite restricted with access. So they can't shape whilst actually cutting with that guide to shape the actual orbital floor in the area for the nasal cavity. So that guide's purpose is just to cut out a block of bone from the pelvis, which is roughly the right size that they can then shape further down the line. So that's the initial guide, which looks often like this. So they would just put it on and cut out a straight block. Then we can do a shaped guide. So to determine this shape, we can overlay the native maxilla that was there in freeform, so I can have both visible at the same time. And then I would use a plane and the sketch tool to draw a natural curve that would match that orbit that was there before, in both the nose and the eye area, and then cut this guide so that we end up with the nice curve shaped, which for this case has been covered in a titanium, just so that in theatre when they're operating it doesn't cause them to cut into the actual plastic itself.
I see.
It just ensures that they can do a natural curvature shape of the bone.
So if you wouldn't mind just talking us through, Millie, the process for creating the orbital floor. Yeah,
so the orbital floor is a really important part of the reconstruction. So this is made from the titanium metal. The purpose of the orbital floor in the first place is to keep the globe of the eye in a stable, steady position and allow it to move freely. Without that, the patient would have problems with their vision, which obviously you don't want. So trying to recreate that natural eye position that they had before is really critical. So to do that, using the CT from the beginning, we can draw in on the software the bones of the orbital floor. They're very thin, so they often don't get picked up on a CT scan. So I would manually draw those in to the non-defect side, and then in freeform we can mirror this over then to the defect side, manipulate it slightly with the smoothing and the wax tools to make it blend in, and then a plastic piece would be printed of the orbital floor then, which in the lab they would mould the titanium metal plate to, and this has then got the drill holes which drill into the new reconstructed pelvic bone that is in place.
Wow. And how long does the operation take approximately?
So on average it's about a 10-hour operation.
Okay.
So it can vary obviously. If there are problems had throughout, it can go for longer, but on average it's about 10 hours, which has been significantly reduced by using the vertical surgical planning. Without that it would have been a lot longer, because they would have had to guess work the reconstruction size. There would have been a lot of back and forth of shaping it and trying to make it look as good as possible, whereas now they've already pre-planned what they want. So by using these guides, it gives them an accurate representation of what they want to do and cuts a lot of time and saves a lot of money in theatres.
Streamlines the process more.
Yeah.
And so for the patient then, in this particular case, how was the patient afterwards, and what was the recovery time?
So the patient is really well. They are still doing really well now. They haven't had any reoccurrence. So it's really good news.
Fantastic.
Recovery can take a while. Speech is obviously affected in these kind of cases. One thing that, because you're taking the roof of the mouth, that's another reason that the pelvis is a good bone to take, because you can take a lot of muscle with it, and the muscle is then used to recreate the roof of the mouth. So underneath, this would all be recreated with the muscle. That allows better speech and allows them to eat and drink better after, which again is making the recovery slightly quicker.
Slightly quicker. Fantastic. What was the feedback from the surgeon?
So the surgeons really love the work that we do, and having an in-house engineer to them is the perfect solution, really. It allows them to be involved, which they really like to be involved. Our surgeons love that they can have an impact in what they are, the cases they're doing, and the design is also got some of their ideas in it. And the fact that they can provide feedback as well, they really like, and they are very keen for me to attend the theatre cases as well, because they like to share like how the work we're doing is being used in theatre and how it is of an advantage to the patient.
Okay, so we've talked about the maxillectomy here. Maybe it's worth talking about other cases that you've done and obviously used the 3D technology.
Yes, so we've done a few cases with orthopedics, cancer related as well, where we've provided cutting guides for resection of tumours in the lower limbs, especially normally the tibia, and that involved working out a whole new design, because it was very different to the workflow that we've sort of streamlined now for the head and neck cancers, because we do so many of those. It was thinking outside the box of the different challenges that were faced.
Okay.
For example, they use a lot of different heavier duty tools in orthopedics surgery, so the guides needed to be stronger necessarily than the guides that we'd been making for the head and neck. So changing things like the thickness in freeform of the guide that we were designing in the first place, adding cylinders to the cutting guides for drilling in K-wires, things like that.
Okay.
So it was adapting and learning new tools that we can add, really, different offsets again, because they were all different. We've also done cases at the Children's Hospital for craniosynostosis cases for children with abnormal skulls where they've fused prematurely. So we've had to use a lot of mirroring, trying to move the pieces around on freeform to recreate a normal looking skull shape. That is the objective of the surgery. So freeform has been very useful again with being able to duplicate those original pieces, move them around, being free, which is again is the point of that software. It's very allows the user to do anything that they want, is what I find. I'm not restricted compared to some kind of CAD engineering software, which can be a lot more limited. It's very user friendly for the freeform.
Fantastic. Josh, question for you is, what improvements or new features are you looking forward to seeing in the haptic?
Specifically for the Touch X, we have been looking at taking it from a 3 degrees of freedom to 6 degrees of freedom, where there will be additional motors on the stylus that'll help constrain the position of the stylus such that you can work in tighter spaces and more real-world type spaces. So in this case here, as you're getting down into the skull and the bone, if you're working in a particular area where there's fine geometry of the human anatomy, the stylus could be contained such that it doesn't move freely within that given geometry. Currently you can still do this with the 3DOF, but it's more of a simulated type deployment of the concept rather than physically constraining you to a given workspace. Some other areas that we are looking at is completely redesigning the Touch X itself, such that it has a lower profile. One of the biggest cumbersome aspects of the haptic device is that it can clip some of the viewing on the screen because of the height of the device. So making it a lower profile device that can fit underneath a technician's or a designer's screen has been a big request for many of my customers.
Fantastic. Thanks, Josh. So how do you see 3D technology evolving in the future, especially in healthcare?
There are cases that we have heard from other designers around the world that tell us that there are specific things that they cannot do in their current CAD software. But with the incorporation of the Haptic plus Freeform software, not only can they do it, but the projected time to actually do it is significantly reduced. We've heard cases where it would take a month for them to complete a surgical planning, and with the Haptic and Freeform, it cuts it down to just a couple of days. There's other cases where it may take several hours, as Amelia said earlier. You can do it in maybe less than an hour kind of situation, and it's all because of the Haptic plus Freeform. There's other areas where I have seen virtual surgical plans where they have a simulator for the actual surgery, and so they take the patient data and all the cutting guides and everything that they created in Freeform, they pull it into a simulator, and the surgeon then practices the actual surgery using the patient data, so that they can not only understand how to do the surgery on this particular patient, but also improve or reduce the time for the actual surgery even further than what they can do with just the parts that are created out of Freeform.
Fantastic. Okay, so I think finally then, for hospitals that aren't using 3D technology, what are the biggest reasons to start?
I think a lot of it comes down to funding, really. We're very fortunate that we've got an in-house engineer position. Some other departments in other hospitals have someone who does it, but it's not their full-time role. Okay. So they're sharing it amongst their workload elsewhere, so they might not have as much time to dedicate to developing the service like I can, and constantly improve the designs, attend theatre, things like that. They don't have as much time, really. I think that's mainly what it falls down to.
Okay. Thank you both for joining us today, and thank you all for listening.
Thank you.
Thank you.